Have you ever stopped to ask, what exactly is nothing? Is a vacuum truly empty? Contrary to intuition, the answer from quantum physics is a resounding no. Today, we're diving into vacuum energy, the quantum engine beneath reality. It's a topic that not only forces us to rethink the fabric of space, but also challenges the way we define energy, nothingness, and even existence itself. So, grab your intellectual compass. This will be a ride into the weird and wonderful realm of advanced physics. All right, let's start at the basics, at least by quantum mechanics standards. A vacuum, in classical physics, is essentially an empty space, a box where you've removed all particles, photons, electrons, everything. But according to quantum field theory, even if you remove visible particles, the vacuum is far from quiet. It seethes with a roiling sea of virtual particles popping in and out of existence at unimaginably small scales, only to vanish as quickly as they appeared. These ghostly visitors are called virtual particles, and their brief existence owes itself to one of quantum physics' stranger loopholes: the Heisenberg uncertainty principle. The uncertainty principle states that you can't precisely know both the energy and the time of a system simultaneously. This fuzziness in nature permits these virtual particles to borrow energy from the quantum vacuum momentarily. As long as they repay it swiftly enough, they're allowed to exist briefly without violating the conservation of energy. It's as if reality itself turns a blind eye to these fleeting violations, simply because they're too fast to catch. Now, you might think, big deal. Particles that flicker momentarily and disappear? Why does that matter? Here's the kicker. Even though virtual particles are short-lived, their collective effects stack up. This is where vacuum energy emerges. Imagine a constantly simmering quantum soup underlying everything. This quantum buzz exerts a measurable force on the macroscopic universe. It's not just theoretical. Experiments have confirmed its reality. Take, for instance, the Casimir effect, a phenomenon first predicted in the 1940s. When you place two uncharged, flat, metallic plates incredibly close together in a vacuum, something astonishing happens. Quantum vacuum energy creates a subtle but measurable attractive force between the plates. Why? Because the plates restrict the wavelengths of virtual particles that can exist in the gap. In other words, the quantum vacuum exerts pressure. This force has been experimentally verified, lending definitive proof that vacuum energy isn't just some arcane theoretical construct. It's as real as the gravity pulling us down. And here's where things get even weirder. If vacuum energy is everywhere, permeating the universe, why doesn't it overwhelm everything? This conundrum lies at the heart of one of physics' biggest puzzles, the cosmological constant problem. When physicists calculate the energy density of the quantum vacuum using quantum field theory, they find an absurdly large number, something like 10 to the power of 120 joules per cubic meter. That's one followed by 120 zeros. But when we measure the actual energy density of space, say, by studying the accelerated expansion of the universe, we get a number that's vastly smaller, by 120 orders of magnitude. Think about that. The theoretical prediction doesn't just overshoot the measured value by a little bit. It's such a mismatch that it's been deemed the worst theoretical prediction in physics. Why the enormous discrepancy? Is it a calculation error? A missing piece of physics? Or is our understanding of energy itself fundamentally flawed? No one knows. Solving this mystery could well revolutionize not just cosmology, but fundamental physics as a whole. It might take us closer to a theory of everything, a unified framework for combining quantum mechanics and general relativity. But what's the physical significance of this vacuum energy besides spawning virtual particles and creating exotic phenomena like the Casimir effect? Well, here's where quantum vacuum energy breaks away from mere curiosity into the territory of profound implications. Some physicists suggest that it could serve as the engine for dark energy, the mysterious force driving the accelerated expansion of the universe. You heard that right. The invisible energy buzzing through every corner of the cosmos, may not just sit idle. It could actively shape the destiny of galaxies, stars, and space-time itself. This kind of speculation fires the imagination. Let's think beyond physics for a moment. If vacuum energy is ubiquitous and potentially harnessable, could it serve as a resource for advanced extraterrestrial civilizations? Theoretical physicist Michio Kaku often speculates about Kardashev Type 2 or Type 3 civilizations, not just planetary or star-scaled societies, but galaxy-spanning ones. In his framework, these civilizations would have the technological prowess to extract energy from something as esoteric as the quantum vacuum itself. If we human beings could ever replicate this feat, it would transform how we think about powering our existence. Free, limitless energy sourced from what appears to be emptiness? It sounds like the realm of science fiction, but it's not entirely impossible in principle. And what about applications here on Earth? Could we one day engineer technology that taps into vacuum energy? The prospect is tantalizing but fraught with challenges. Right now, our understanding of vacuum fluctuations and their energy is nascent, constrained by experimental limitations and incomplete theories. Yet some speculative schemes, like harnessing quantum fluctuations with advanced nanotechnology, are emerging in the scientific literature. If successful, it would represent a new frontier for energy science, moving us beyond conventional fuels and even renewables into a deeply quantum realm. But let's temper our optimism for now. No one has yet demonstrated practical ways to extract usable energy from the quantum vacuum without violating the laws of thermodynamics. Now, let's pause and zoom out for a moment to contemplate the philosophical implications. Isn't it extraordinary that what we once thought of as nothingness, absolute void, is in fact teeming with energy and activity? It forces us to question the very dichotomy of something versus nothing. Vacuum energy stands as a humbling reminder that our intuitive notions of emptiness are merely shadows of a deeper, richer reality. Moreover, the fact that this energy may underpin cosmic expansion makes it a central piece of the puzzle of existence itself. Could it point toward the idea that our universe is self-generating, building its complexity out of interplay between simple quantum rules, acting on a profound emptiness? Or does it hint at an underlying structure? Could there be layers, a lattice, or some organizing framework hidden beneath the chaos of quantum noise? These questions scratch the surface, but they show why the quantum vacuum isn't just another technical curiosity. It's a door to profound insights about reality. So, where does this leave us? First, it's clear that vacuum energy is no trivial phenomenon. It reshapes the way we think about the most fundamental aspects of the cosmos, challenging us intellectually and inspiring new directions for theoretical and experimental research. At the same time, it reminds us how much we don't know. Why are the theoretical and observed energy densities so wildly different? Can we reconcile quantum mechanics and general relativity to crack the enigma of the quantum vacuum once and for all? Until then, the vacuum retains its mystique, a tantalizing void brewing infinite possibilities. Before I wrap up, let me ask you, what do you think the ultimate significance of vacuum energy could be? Could it power our future, or are we destined to marvel at it from afar? Share your perspectives in the comments. I'm truly curious to see how you engage with this mind-bending topic.